you had to look at R5. Rock and roll. General answers. These general answers hopefully will we'll turn them into more specific answers right now. So on R5, you should have analyzed it last night. Can someone tell me what the numerator factors into? Someone raise their hand. Go. Yeah.
X minus 2 times x plus 1 times x plus 3.
Who agrees with that? Agree? Disagree? Agree?
Agree.
Yay! You're popular. Denominator. Who wants to factor it? Chamberlain, go.
X plus 3, x minus, plus 5, and x 10.
Awesome. What could we have figured out immediately from this? What could we have figured out immediately? It has a horizontal asymptote. Why? I need you to be more specific.
Because
The powers of the pony outside?
of the leading factors are equal.
The highest power in both the numerator and the denominator are equal.
That is correct. That was very specific. That's exactly what I wanted. The degree of the numerator is equal to the degree of the denominator. Which powers?
Power 3.
Exactly, but when you just say the highest powers are equal, the highest powers of what? I need you to be really specific. So we know it has a horizontal asymptote, so when the powers are equal, what do you look at once you know the powers are equal? You look at the leading coefficients. In this case, the leading coefficients are... So what is the horizontal asymptote? No.
X equals 1.
No.
Y.
Y equals 1. X, Y, A, B. Oh. What is the land speed of the average swallow? One person. It's not bad. So after that's just a nice side note. Well, that also tells us, what about oblique asymptotes? None. There are none. You know that. It's good. There are none. So at this point, no questions yet. Step 1. And now let's just start calling people out. Hector, can you tell me what the domain is?
The domain is x is not equal to -3, -5, and 1.
Yes. X such that x is not equal to those things. Exactly. Can someone tell me, break this down a little bit. Andy, can you tell me one of the intercepts? 0 what? Yes, because -6 over -15 is 2/5. Correct. Can someone tell me, he's not here, can someone tell me, Anna, can you tell me one of the other intercepts? Yep. 2 what? 2 is a number, not an intercept.
Yeah,
2, 0. Exactly. And there's one more. Baker. What? What's the last intercept? There's another x-intercept.
Yeah,
So we've taken care of this one. What's left? Yeah, exactly. Is there another intercept? No. Ah, it's not included in the domain. It crosses out. Exactly. It's not part of the domain. What about symmetry? And we'll talk about, let's go to Anna.
Symmetry?
Yep. Just look at it. Look at the equation.
It's not.
It's neither, yeah. In most cases that we look at, is there going to be any nice symmetry? No. Is it going to be just a really nice surprise sometime? Always check it. It's a really nice thing when it happens. That tells you a whole lot about the function, because basically something's symmetric across the origin or the y-axis. You only need half the graph, and then what can you do? Flip it over. Exactly. Okay, so let's do vertical asymptotes. Can someone, can you tell me one of the vertical asymptotes? One of them. Bingo. Good job. Zach Cochran, can you tell me the other one? Okay, it's fine. It's fine. You're going to have to, we know, we got to check in. Felicia. Are there any others? No, because do we have this? At what? And we're going to go to Brooke.
-3, -5/4.
Yeah, and where'd you get the -5/4 from?
By plugging the 3 back.
-3. Back into the simplified, the fully factored simplified form. So if you cross this out, what crosses out? I gotta erase that. The x plus 3 crosses out, this crosses out. Now you plug in -3, and you end up with -5/4. Awesome. So what's left here? We have HA. Oh, we already know that. It's y equals. and oblique. Now, what's the last thing we need to check?
How do we
When
know
it
that
crosses
it's
the horizontal.
You can't have both.
okay?
When
Oh,
it
that's
crosses
right.
the horizontal.
Crosses the horizontal. Okay, we have two things. We want to see if they intersect. A graph of something is a visual representation of the solution set. So if this is the visual representation of the solution set of one function, and this is the visual representation of the solution set of another function, what does the intersection point represent?
Where they're both
When they
equal.
have the same value.
No, not yes, they're the same value. It's a solution to both. If this is the solution set to one set of one equation, and this is the solution set to another, the intersection is a solution to both. So if you want to find the intersection of two things, you set them
Equal to each other.
and do you set the factored form or the original?
Original.
Please use the original. You use the original because it's closer to what you want. You want to be able to cancel stuff out. And in this case, what do you set it equal to?
1.
Yes. You want to know when this is equal to 1. And that happens when this is equal to this. What cancels?
Cubed x.
And then that combines there, and you end up with 5x squared. This combines there, and you end up with
No.
No.
negative what? And this is 0. You got a quadratic. You love quadratics. Yeah.
We have to intersect.
We have 2. Oh, 2 or 0 or 1, right? Could be anything. How do we solve a quadratic? Yes.
I should really know this, but why did you set it to 1?
Because the horizontal asymptote is 1. And it's nice. Constants are great. Constants are great because then you end up with a nice, direct relationship. We hope that this is what? Should we play the factoring game where I count out random numbers and you try to factor?
No.
That was fun.
No.
That was fun for me. Was it fun for you?
No.
It was great. I think there isn't enough stress in school. We need to actually put some more into there. What? What? Teachers enjoy that? What? This is nicely factorable, I'll tell you that. Can someone tell me what it is? 5x what? Minus 3 and x. Yeah, there you go. So what does x equal? 3/5 or? Ah. Bing, 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 bing. Something's wrong. We did the math right, but what do we have to not?
You can't include
can't
negative
include
3.
Thank you for remembering that. You always need to remember what? Remember domain, so I like to call it remembering reality. You can't plug in negative 3, so can you have an intersection point at negative 3? No, you actually know what's happening at negative 3. What is it? It's a removable discontinuity. Can you have an intersection point at a removable discontinuity? No, because by definition, it's removed. It's not there. There's nothing there to intersect. This is a false answer. We've seen this before. When you square things, it is possible to get answers that aren't correct, even if you do the right math. You can generate false answers.
That just open dot thing.
It's an open dot thing, exactly. This is an open dot right here. So we just found, but the intersection point is an actual intersection. So how do we figure out where it intersects? Well, this point was that's the x value where the function intersects what line? Y equals. So what's the y coordinate? 1. Don't forget that, because this is what you might do. When you have an x coordinate, how do you generally find the y coordinate? Plug it back. So people do this, like, oh man, what do I have to plug that into? This. And I don't have my calculator. I hate Mr. Seamon. It's stupid. And then they do it right, and they get 1. And then they're like, oh.
It's 1 because that's the...
You're trying to find the intersection. We're trying to find the intersection of 1 on the y-axis, on the y-coordinate, and some crazy thing. Wherever the crazy thing intersects, what's the y-coordinate going to be? 1.
Because of the
Horizontal asymptote. That's what we were trying to solve for. We now have a ton of information. Are you ready to draw a picture?
Yeah.
Let's draw a picture. I love drawing pictures. Am I interested in something that's super duper unbelievably accurate?
No.
General drawing here.
There's like a part of the graph that is come out there.
You have to use. Well, I'll show you what's going to happen. I'm going to draw this wrong. I'm going to shrink it and move it around. It gets really annoying. It's hard to do because as you're piecing this together, you might realize you need, like, dang it, I need something over there. This is what I'll tell you. Change the scale at will. That's totally fine. As long as you label your points, I'm happy. And as long as it generally looks like what I'm looking for. Because to graph these really, really, really nicely, sometimes proper scale looks the worst. I'll show you what I mean. We have intercepts. What were they? I think the y-intercept was what? What is it? 3/5? 2/5. And then it's at, it crosses at 2, right? And what? -1, correct? And we have a vertical asymptotes where? 1, right? There's x equals 1. Where else do we have one?
Horizontal and y.
Well, negative 5 as well. It's going to get both vertical ones in first. Like that. Again, not to scale. X equals negative 5. We know vertical. And we know that there's a horizontal asymptote at what? 1, right? So I don't know, like right here. Is that it? We also know it crosses y equals 1. Where does it cross y equals 1? At x equals 3/5. Or I don't know, like right there. So at right here, it crosses. So at that value, it crosses. And there's one point we haven't graphed yet. What is it?
Removal continuity.
Removable discontinuity, yeah. And that's at negative 3, negative 5/4, right? So negative 3, I don't know, right about there, and negative 5/4. So what do we have right there? Open dot. We've graphed everything we have. What should you do now? Connect the dots. I'll tell you this. We know it has to go up like this. Why? Can't cross the vertical asymptote, and it can't go down. Why? If it went down, what would it cross?
The x-axis.
Is it allowed to cross the x-axis? No, we found all the places. Where does it go to on the left? It has to go infinitely close to the removable discontinuity. So what's it going to do here? It's going to continue down. So now we're going to answer that question. How do you know the other sides? How do you know what it looks like? Here's the thing. Has our domain been satisfied? Well, we're not using negative 3. We're not using negative 5, and we're not using 1. So is our domain okay so far? But we need to know what's going on here and what's going on here. How do we figure that out? You look at, well, there's one point we haven't crossed through on the right. What's that? 2. So what does it look like on the other side? Lots of gravity. Ooh. How do you do that? Is there any other thing it can do?
There's no other place where it crosses.
It can't go back down. It has to do that. Is there any way to do that so can it cross the blue line anywhere else? Could this thing spike up and down? No, because we...
Very
Ooh.
crossed one.
Hold on. Ah!
Okay.
There we
Oh, I
go.
hope that goes into the
Oh,
remix.
it's definitely there. That's why you're going to watch the videos, huh? The remix? Yeah. So, yeah, with all that time I have. I feel like time is moving backwards because as I think
really
of...
like to stress teachers out.
I do, but I'm a
don't-
much better actor and liar than you are.
Students like to stress.
I know. I heard you. I'm just saying that it's very hard to tell how stressed I actually am sometimes. I'm actually thinking about Tolstoy right now as I have this conversation with you.
About what?
It's so easy to confuse you. And I mean you here, the royal you. We need the other side. How do we figure out the other side? Well, we can do a few things.
Multiplicity.
We can look at multiplicity. Let's say we knew nothing. We could do what?
Plug in a value.
We could plug in a value. If you ever get totally stuck, don't forget this. If you have no idea what's going on, pick a value over here. So what value could we pick? Plug negative 6 into it and see where it is. We could do that. We're going to look at multiplicity now, though. Let's look at the multiplicity. We look at the multiplicity of the factors that result in vertical asymptotes. What's the degree of each of these terms? What's the degree of x? 1 and 1. Both of those have a even multiplicity. The degree of the whole term. These numbers right there.
They're even.
They're odd.
Why did you get rid of the one?
I don't know. Just let me have some, please. Please.
Look at the overall, like the overall.
No, you're looking at just that term. Because to analyze the behavior of a graph around negative 5, what's the only term that's really going to matter around negative 5? X plus 5. Because interesting thing, what happens to x plus 5 around negative 5? It becomes 0, but we know it can't be 0 because we can't plug it in. To make,
Infinite.
it gets really close and becomes negative, and then instantaneously it switches to positive. Here's negative 5, right? What kinds of numbers are to the left of negative 5? Maybe negative 5.1? What's negative 5.1 plus 5? Negative 0.1, right? And that's a negative value, right? What happens if you're to the right of negative 5? You're at like negative 4.9? What's negative 4.9 plus 5? Positive 0.1, right? So it went from negative to positive. Do any of the other terms that make up that rational function change from negative to positive? At negative 5. Do any of the other ones change sign? No, because the only x plus 5 is the one in that denominator. So around, this is a big idea here, so it's really okay if it takes you a while. Around negative 5, x plus 5 changes sign, And what's that going to do to the overall function?
That?
All of a sudden, it's not infinitely going down. It's going to be. That's why you have a spike like this. There's this big blip. Does that kind of make sense? Everything else dictates over here. So look. Wow, that was cool. No, really, awesome. Live for that. Look over here. So this is responsible. X minus 1 is responsible for the asymptote x equals 1, right? What happens around 1? X minus 1 changes from positive to negative, meaning the graph is going to spike up and down. What happens around negative 5 at x plus 5? Same thing. So it goes, 1 goes up, 1 goes down. But what happens if it was squared?
Oh god.
Both would go up or both would go down, because look, x minus 1 squared is always going to be positive. It's always going to be positive, right? When you square something, it's always going to be positive. So if I square something and multiply, if you have, let's say this table represented some crazy function that did crazy things, right? If I put something squared attached to it and multiplied by it, and that thing is squared, can this thing change the overall sign of this?
True.
This is always positive. This is always positive. Can something that is always positive change the sign of something else? No. So therefore, if you're squaring a term, the asymptotes on each side, you're going to approach it both going up or both going down. Like if this whole table is negative and I multiply by a positive, it stays, negative.
Okay.
That's why both could go down.
Okay.
So going back to this, both have odd multiplicity. So therefore, it has to go up and down. So over here, it has to go, it goes down here. We know it has to go down there. So what does the other side do? It has to go up. So what does this look like? Can this thing cross?
It has to go up and down.
Up and up. If that's an even multiplicity, so for example, what would happen if it was x plus 5 squared in the denominator? Both would go down.
And then we'll go up, right?
But no, it's odd. Look, it says it right here. Look, ready? It's odd. It's 1. The power of this is 1. It is odd. So therefore, at negative 5, the approach is going to be down and up. So going back and looking at this, we knew for a fact that it had to go down right there. So on the other side, it has to go up. So take a look at this picture. How do we feel about this picture? It's pretty scary, but remember this. You can always plot a point, and please do it one little thing at a time. Yes, and then yes.
Okay, so and it won't cross the y equals 1 because we can only cross at the...
Exactly. We know it can't, theoretically, the function could go down and go up like that, but we know it only crosses it right there. Can't cross it anywhere else. And by definition of a function, it can't cross the yellow because it would cross a vertical asymptote. Can you do that? No, can't do that. Asymptotes have a lot of gravity. They pull things back eventually. Yes, and then yes.
The one that we already knew on.
This one right here? Oh, the one we already knew?
Yeah, that one.
Yep.
We knew that one goes up and down.
Because if it went up there, it would have to cross, right?
Oh,
And,
okay.
yeah.
Yeah.
And it's the same thing for the other side.
Yep.
So,
Yep, exactly.
So they
Very
can
good.
only cross, those lines represent asymptotes.
Asymptotes.
And you can only cross them.
Where we solved it. We solved right here. Look, we did the math.
And so you can only cross it once.
No, you could theoretically set one of these up to cross many times as you want, but look, we did the math and it came out it only crossed at 3/5.
Okay.
So it means it can't cross anywhere else. So it means even if you want to, it stays away from it.
Yep. Okay.
So I want to show you at this point, this is the segue I want to use. No, Iverson, but I got to thinking last night, there's a lot of other, there's some tools that I want you to be conscious of. The remix, every now and then he just blinks and says, practice. Here's the first thing I want to show you. There is a great website called Fooplot. It's going into the notes. You do not have to remember it. It's just a website, and I just lost it. Load it back up again. Here it is. It's an online grapher, and it works really well. So, for example, there's sine x. How about I do cosine x, and just press enter. Oh, there it is. Let's say I wanted to zoom out. Let's say I wanted to pan. Right? Sound good? What happens if can someone tell me what the numerator of the function we just graphed is? X what? X cubed what? Hannah, read it to me.
X cubed plus 7x squared.
Slowly, 7x squared.
Plus 7x.
Plus 7x, yep.
Minus 15.
Minus 15.
What's the denominator? That's what you want, right?
Nope. But what's the numerator? What's the numerator?
2x squared.
2x.
I'm sorry, x cubed plus 2x squared.
Shh, x cubed, I know this is hard, plus what? 2x squared.
Minus
Yep.
5x.
Minus 5x, yep.
Minus 6.
Minus 6. Great. Watch this.
Whoa.
And let's change the color. I want to change it to, let's cut that and put it right there instead. Boom. And let's zoom out a little bit. Does that match our graph?
Yeah.
It does. You have to take things with, you have to analyze this a little carefully. Are these vertical asymptotes actually there? No, it's connecting dots is what it's doing. So it goes zip and it connects it down. Does it calculate every value? No, that's impossible because how many values exist between any two numbers? An infinite number. So it plots a certain like density and it connects them.
So
Does this actually stop right here? No. If I zoom in, it keeps on going up. The reason it looks like it stops is it can't quite deal with the resolution. It's a very steep curve, so it just stops. It's not. You can think of it as an error, but it doesn't have the resolution to graph that. So what's nice about this is you can really easily make graphs, and then you see down here you can download it as an image file. You can graph things more than once. So for example, here's how it could be used in this case. Let's zoom out a little bit.
Is heart rate rational function?
Is what?
heart rate.
It could be. I think you can model it with some oscillating rational function. What could we also put in? How about y equals 1? Look what that. Do you see it? Can you turn the light off?
Light is on.
Oh, it is off. Can you pull this down gently, Danilo? Gently. Really gently. Look what I did there. If I put this in, if I put y equals 1 in, and press enter, take a look. Does that match what we think it should do?
Yeah.
Yeah.
So you're saying that those big vertical drops aren't actually real?
No,
it's just-
the lines aren't there. The vertical lines aren't there. Those you can think of them as representations of the vertical asymptote.
Okay.
Can you plug any function you want into this basically? Yep. Pretty cool, huh? So then you can save this. So this is fooplot.com. I will put this into the notes. Second thing I want to show you is has anybody seen this site before?
No.
Quickie. It's brand new. It just launched. This is you can think of this as a really interesting front end to Wikipedia. What it does is you put in a topic. So for example, it pulls the text from Wikipedia and it pulls images from all across the net, and it does something really kind of interesting that I'm a fan of. It takes a second for it to load. Just watch.
Oh, cool.
Wait.
During his lifetime, he published more than 600 scientific papers and popular articles and was author, co-author, or editor of more than 20 books. In his works, he advocated skeptical inquiry in the scientific
So
method.
this is a great launching point if you want to learn about something quickly, hence the name. It pulls together some great material and it works really well. So if you want to figure out something really quickly, put it in, pulls it out, reads it to you. I found it was I sat there for like a while just typing terms in, and then you can go through this text here. It's as it scrolls up, and anything that's blue you can click on. So later it talks about this woman right here.
Marvelous, mother of Dorian Sagan and Jeremiah Sagan.
So you can click around like you're clicking around inside Wikipedia. You can do the same thing here. My quick story was that when I was, this is pretty neat. So what's something we want to calculate or know about? What's something we want to calculate or know about? General.
Taking square roots by hand.
Want to know about, so how about something more general? Something data driven. Something else, yeah? Population. What's the population of what?
Montenegro.
Okay, let's try it. Like that. It goes out and does some fun stuff. Assuming Montenegro is a country, results 62,000 people. It gives you recent history, gives long-term population history, population growth rate, approximate heat production. Gives you a ton of stuff, right? Okay, something else. Someone give me something else we want to know about. Something numeric. Something else numeric.
Times of the fastest Olympic runners.
How fast can a human run? How about that? Just something general.
In vacuum.
In a what? In a vacuum?
You know,
Not very
I would
fast.
imagine running.
Results. 7, as Usain Bolt. Unit conversions. Human max speed on land, right? Give me one more. Someone give me something else. Yeah.
Like the amount of dollars in circulation.
Yeah, that's a great one. How much USD is in circulation? Yeah, I can see this. I'm not typing very well. Oh, that's nice. How much money is in... Can someone spell circulation for me?
C-I-R-C-U-L.
That's a great question. I wonder what it does. How much USD is in circulation? Some of the other stuff takes a little while. A formula. I didn't quite get that one. It's not always perfect. It's not always perfect. How about... give me one more thing.
What if you were US dollars?
How much does a polar bear weigh? How much does a polar bear weigh?
It's
When
in
she's
one of my
12, when she's
monologues.
12.
There it is. Unit conversion. It gives you the scientific name, max weight, max recorded weight. Stuff like that. Pretty neat, huh? Anything else more complicated? Let's throw something more complicated at it.
How many times does Allen Iverson say practice?
Can you please try that?
No, hold on. I want a computational knowledge. What's the tax rate in the United States? Let's see what it does with this. The more general has a little trouble. Individual tax as a percentage of AGI. Look at this. Tells you adjusted gross income. It's telling you exactly. Look at this. This is amazing, right? Yeah, watch this. Here's the punchline, everybody. That says 2x squared plus 5x plus 3. Input. It tells you it's a parabola. It gives you a larger graph. It gives you a smaller graph. It gives you the alternate forms. It gives you the roots. And later, when you take calculus, it tells you all this stuff. In addition, it does this stuff. Show steps. Oh, look. It shows you the steps. Okay, it's even more fun. What am I copying into it? Don't go anywhere. Here's the rational function that we just looked at. Boom. Input. It graphs it. Look what it did. Look what it did. What did it do? And simplified. And it gave you the roots. And it gives you all this other stuff. Is that a pretty fun tool? So, listen, your homework, everybody. Your homework. Just so I'll say it out loud so you know what it is. Your homework is verify all of the information about R6. So we didn't do this group activity, but it's fine. On R6, basically, I want you to graph R6 by hand. That's what I'd like you to do. Graph R6 by hand. Second thing I want you to do, play around with the 3 web tools of the day and come in with at least 2 cool facts about each. And watch Rational Functions Part 6. Watch Rational Functions Part 6.